When dealing with a 100 amp panel feeder and encountering voltage drop issues necessitating the use of 2/0 conductors, along with the presence of nonlinear loads requiring a double neutral, the situation becomes more complex due to conductor field derating. With 5 current carrying conductors plus a ground in the raceway, the National Electrical Code, or NEC, mandates derating the conductor ampacity by 80%. The question arises whether increasing the wire size to 4/0 is necessary to compensate for the 80% field derating, or if 2/0 is sufficient since it is rated well over 100 amps. The NEC addresses conductor ampacity, derating factors, and conduit fill requirements to ensure electrical systems operate safely and efficiently. Firstly, it's crucial to understand the concept of ampacity, which refers to the current carrying capacity of a conductor in amps. The ampacity of a conductor is determined by several factors, including its size, material, insulation type, and the ambient temperature in which it operates. Conductors are typically made of copper or aluminum, with copper having a higher ampacity for a given size compared to aluminum. Insulation types, such as THHN, THWN, or XHHW, also affect ampacity ratings, as they determine the conductor's ability to withstand heat generated by the current flow. Secondly, derating factors come into play when conductors are installed in conditions that reduce their ability to dissipate heat. One common reason for derating is conduit fill, which refers to the percentage of the raceway's cross-sectional area occupied by conductors. When the conduit fill exceeds 40%, the NEC requires derating the conductor ampacity to prevent overheating and potential insulation damage. The derating factor is based on the number of current carrying conductors in the raceway, with more conductors resulting in a greater reduction in ampacity. Thirdly, the NEC specifies the allowable ampacities for various conductor sizes and insulation types in tables such as Table 310.15b16. These tables provide the maximum current a conductor can carry under specific conditions, such as a certain ambient temperature and number of conductors in a raceway. However, it's important to note that these ampacities are based on ideal conditions and may need to be adjusted based on derating factors and other considerations. In a given scenario, the presence of nonlinear loads introduces additional complexity. Nonlinear loads, such as electronic devices and LED lighting, draw current in short, high-amplitude pulses, which can create harmonic currents in the electrical system. These harmonic currents can overload the neutral conductor and cause overheating, which is why a double neutral is required in this case. A double neutral provides a larger current carrying capacity for the neutral conductor, reducing the risk of overheating and ensuring proper system operation. If in the presence of 5 current carrying conductors plus a ground in the raceway, the 80% derating factor must be applied to the conductor ampacity. This means that the actual ampacity of the 2/0 conductors is reduced to 80% of their rated value. To determine whether 2/0 conductors are sufficient after derating, it's necessary to consult the NEC tables and perform the appropriate calculations. Let's assume that 2/0 conductors are made of copper and have THHN insulation, which has a typical ampacity of 175 amps at 75 degrees Celsius. Applying the 80% derating factor, the adjusted ampacity of the 2/0 conductors becomes 175 amps multiplied by 0.80, which equals 140 amps. Since the panel feeder is rated for 100 amps and the derated ampacity of the 2/0 conductors is 140 amps, it may seem like the 2/0 conductors are sufficient. However, it's crucial to consider other factors, such as voltage drop and future load growth. Voltage drop refers to the reduction in voltage along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and reduce overall system efficiency. The NEC recommends limiting voltage drop to 3% for branch circuits and 5% for feeders. In this case, the long length of the panel feeder and the presence of nonlinear loads can exacerbate voltage drop issues. Therefore, it's essential to calculate the voltage drop using appropriate formulas and consider increasing the conductor size to minimize voltage drop. Furthermore, it's important to consider future load growth when selecting conductor sizes. Electrical systems are typically designed to accommodate future increases in load, such as the addition of new equipment or appliances. If the panel feeder is expected to serve additional loads in the future, it's prudent to increase the conductor size to provide sufficient capacity. In light of these considerations, it's generally recommended to increase the wire size to 4/0 to compensate for the 80% fill derating and ensure adequate ampacity, voltage drop, and future load growth capacity. According to NEC Table 310.15b16, 4/0 copper conductor with THHN insulation has an ampacity of 230 amps at 75 degrees Celsius. Applying the 80% derating factor, the adjusted ampacity of the 4/0 conductors becomes 230 amps multiplied by 0.80, which equals 184 amps. This provides ample capacity for the 100 amp panel feeder, as well as potential future load growth. In summary, when dealing with a 100 amp panel feeder with nonlinear loads, a double neutral, and a long run requiring voltage drop compensation, increasing the wire size to 4/0 is necessary to account for the 80% fill derating and ensure sufficient ampacity, voltage drop, and future load growth capacity. While 2/0 conductors may have an initial ampacity greater than 100 amps, the derating factor reduces their effective ampacity, potentially compromising system performance and safety. By following NEC guidelines and considering all relevant factors, electrical systems can be designed and installed to operate safely, efficiently, and reliably for years to come. The NEC, updated every 3 years, provides comprehensive guidelines for electrical installations, covering various aspects such as wiring methods, overcurrent protection, grounding, and equipment installation. It is essential to consult the latest edition of the NEC and local codes to ensure compliance with all applicable requirements. Additionally, it is recommended to engage a qualified electrical engineer or contractor to perform calculations, select the appropriate equipment, and oversee the installation process. Electrical work can be hazardous if not performed correctly, and improper installations can lead to electrical shocks, fires, and other safety risks. Therefore, it is crucial to prioritize safety and adhere to all applicable codes and standards. In addition to ampacity, derating factors, and conduit fill requirements, other factors can also affect conductor selection. These include ambient temperature, conductor bundling, and the presence of harmonics. Ambient temperature refers to the temperature of the surrounding environment in which the conductors are installed. Higher ambient temperatures can reduce the ampacity of conductors, as they have less ability to dissipate heat. The NEC provides correction factors for adjusting conductor ampacity based on ambient temperature. Conductor bundling refers to the practice of installing multiple conductors together in a tight bundle. Bundling can reduce the ampacity of conductors, as it restricts their ability to dissipate heat. The NEC provides derating factors for adjusting conductor ampacity based on the number of conductors in a bundle. Harmonics, as mentioned earlier, are non-sinusoidal currents that can be generated by nonlinear loads. Harmonics can increase the current flow in the neutral conductor and cause overheating. The NEC provides guidelines for sizing the neutral conductor to accommodate harmonic currents. In addition to copper conductors, aluminum conductors are also commonly used in electrical installations. Aluminum conductors are typically less expensive than copper conductors, but they have a lower ampacity for a given size. When using aluminum conductors, it is essential to select the appropriate size to ensure adequate ampacity and voltage drop performance. The NEC provides tables and guidelines for sizing aluminum conductors. When selecting conductors, it is also important to consider the type of insulation. Insulation is the non-conductive material that surrounds the conductor and prevents it from coming into contact with other conductors or grounded surfaces. Different types of insulation have different temperature ratings and resistance to moisture, chemicals, and abrasion. The NEC specifies the types of insulation that are suitable for various applications. In addition to conductors, raceways are also an important component of electrical installations. Raceways are enclosed channels that protect conductors from physical damage and provide a path for them to be installed. Common types of raceways include conduit, electrical metallic tubing EMT, and cable trays. The NEC provides guidelines for selecting and installing raceways. Overcurrent protection is another critical aspect of electrical installations. Overcurrent protection devices, such as circuit breakers and fuses, are designed to interrupt the flow of current in the event of an overload or short circuit. Overcurrent protection devices protect conductors and equipment from damage caused by excessive current flow. The NEC provides guidelines for selecting and installing overcurrent protection devices. Grounding is also an essential safety measure in electrical installations. Grounding provides a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices to trip and de-energize the circuit. Grounding reduces the risk of electrical shock and equipment damage. The NEC provides guidelines for grounding electrical systems. In conclusion, selecting the appropriate wire size for a 100 amp panel feeder with nonlinear loads, a double neutral, and a long run requires careful consideration of ampacity, derating factors, conduit fill requirements, voltage drop, future load growth, ambient temperature, conductor bundling, harmonics, conductor material, insulation type, raceways, overcurrent protection, and grounding. By following NEC guidelines and engaging qualified professionals, electrical systems can be designed and installed to operate safely, efficiently, and reliably. This includes understanding the NEC tables, performing the necessary calculations, and selecting the appropriate equipment for the specific application. Remember to always prioritize safety and adhere to all applicable codes and standards when working with electrical systems. Firstly, the NEC Table 310.15b16 provides ampacity ratings for conductors based on their size, insulation type, and temperature rating. Secondly, derating factors are applied when conductors are installed in conditions that reduce their ability to dissipate heat, such as when multiple conductors are bundled together or when the ambient temperature is high. Thirdly, conduit fill refers to the percentage of the raceway's cross-sectional area occupied by conductors. The NEC limits conduit fill to prevent overheating of conductors. Fourthly, voltage drop refers to the reduction in voltage along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction and reduce overall system efficiency. Fifthly, future load growth should be considered when selecting conductor sizes. Electrical systems are typically designed to accommodate future increases in load. Sixthly, ambient temperature refers to the temperature of the surrounding environment in which the conductors are installed. Higher ambient temperatures can reduce the ampacity of conductors. Seventhly, conductor bundling refers to the practice of installing multiple conductors together in a tight bundle. Bundling can reduce the ampacity of conductors. Eighthly, harmonics are non-sinusoidal currents that can be generated by nonlinear loads. Harmonics can increase the current flow in the neutral conductor. Ninthly, conductor material such as copper or aluminum affects the ampacity of the conductor. Copper conductors have a higher ampacity for a given size compared to aluminum conductors. Tenthly, insulation type affects the temperature rating and resistance to moisture, chemicals, and abrasion of the conductor. By considering all these factors, electrical systems can be designed and installed to operate safely and efficiently.